Today we will do Lecture 6-1 on convolution examples, which is a continuation of Lecture 5-3 on convolution examples. At the conclusion of today's lecture, students should be able to solve the convolution to find the output of a linear time-invariant system. They should still be reading Chapter 5 of the course notes. In the last lecture, we used the analytical integral in order to solve for the convolution, and today we will use a graphical method in order to solve for the convolution. It is a method that's called flip and slide because we will write one, either x of t or h of t, and we will flip and slide the other function along that first one in order to find the result. Let's look at this on in-class activity 1. Determine the output y of t of a system with h of t equal to e to the minus t, u of t minus u of t minus 2, and x of t equal to u of t minus 1. What I will do is draw x of lambda and flip and slide h of lambda. So, x of lambda is u of lambda minus 1. So it's a step function that turns on at time 1 with an amplitude of 1. H of lambda is an exponentially decaying function that starts at time 0 with an amplitude of 1 and dies off and turns off at time 2. So we flip it first, so that's h of negative lambda. So h of negative lambda starts at negative 2 and it's exponentially decreasing to the 0. So that function would be e to the lambda, u of lambda plus 2 minus u of lambda. And then the sliding happens when you integrate h of t minus lambda. So what that means is that t is a variable. Based upon the value of t, this function would slide along the horizontal axis. So for example, if I drew it here, the leading edge is t, and the trailing edge is t minus 2. And as t changes, it slides back and forth along this axis. So this would be e to the negative t minus lambda times u of t minus lambda minus u of t minus lambda minus 2. So now that we know how to create the flip and the slide, let's look at the different regions where we have flipping and sliding over here. There are going to be 3. The first region occurs when there's no overlap between x of lambda and h of t minus lambda. And here would be an example here where this is h of t minus lambda. So this is t and t minus 2, and here's the 1. So for this region, t is less than or equal to 1, and y of t is equal to 0. Okay, our next region would be where h of t minus lambda begins to intersect x of lambda, but h of t minus lambda is not completely enclosed in x of lambda. So here's the 0 and here's the 1. And now we have t. Here, t minus 2. And since it's not completely enclosed yet, we know that the limit of the overlap has to be 3. Because if it was beyond the 3, then the h of t minus lambda would be completely enclosed in the x of lambda. And to help you to understand what I mean here, I'm going to put a sketch of x of lambda here. So this red line represents x of lambda. So for this region, I have t between 1 and 3, and y of t is equal to the integral from 1 to t, e to the negative t minus lambda d lambda. So when we evaluate this integral, we get y of t is equal to 1 minus e to the negative t minus 1. Okay, the final region is when h of t minus lambda is completely overlapped by x of lambda. So once again, I'll sketch x of lambda. This is x of lambda. Here's 0 and here's 1. And now we have h of t minus lambda here. So here's t minus 2, and this is h of t minus lambda. So this region represents where t is between 3 and infinity, or where t is greater than 3. And for this region, y of t is equal to the integral from t minus 2 to t, right, because the overlap happens here, e to the negative t minus lambda d lambda, which equals 1 minus e to the negative 2. And finally, you would write the final answer as a piecewise function. So y of t is equal to 0 for t less than 1 minus e to the negative t minus 1 for t between 1 and 3, and 1 minus e to the negative 2 for t greater than or equal to 3. Let's look at another example. Determine the output of y of t of a system with h of t equal to e to the negative t plus 2, u of t plus 2, and x of t equal to u of t minus 1 minus u of t minus 2 plus 2 u of t minus 4, u of t minus 6. As we did before, we're going to sketch x of lambda, and we're going to flip and slide h of lambda. So x of lambda is a sum of 2 unit steps. So we have one with an amplitude of 1 and one with an amplitude of 2. So the first one turns on at time 1 and turns off at time 2. And the second one turns on at time 4, has an amplitude of 2, and turns off at time 6. H of lambda is an exponentially decaying function that turns on at negative 2. So this would be e to the negative lambda plus 2, u of lambda plus 2. Okay, we will flip it first. So now we have h of negative lambda. So it now has the 2 here, and it decays the other direction, or it's exponentially increasing. And the equation for this one would be e to the negative lambda plus 2, u of negative lambda plus 2. And remember, the t is what causes the sliding. So then we would have h of t minus lambda. So now the leading edge is going to be t plus 2. And the equation would be e to the negative t minus lambda plus 2, u of t minus lambda plus 2. Okay, so let's determine our regions of overlap. The first region is going to be where there's no overlap at all. So this would be for t plus 2 less than 1. So when t plus 2 is less than 1, that's the same as t is less than negative 1, y of t is equal to 0. Our next region would be when t plus 2 is between 1 and 2. So we're going to have t plus 2 between 1 and 2, or t is between negative 1 and 0. And let's draw a graph of what this looks like. So here's 0, 1, 2, and here is h of t minus lambda. And I will put x of lambda in red. And here is that first rectangle for x of lambda. So then our next step would be to find the integral. Recall that the leading edge on h of t minus lambda is t plus 2. So the integral is y of t is equal to the integral from 1 to t plus 2 e to the negative t minus lambda plus 2 d lambda. Our next region is where t plus 2 is between 2 and 4, where it completely overlaps the first block but not the second one. So here's our sketch of h of t minus lambda. And here's t plus 2. So t plus 2 is between 2 and 4, or t is between 0 and 2. So y of t is equal to the integral from 1 to 2 e to the negative t minus lambda plus 2 d lambda. The next region will be where t plus 2 is between 4 and 6, which means that h of t minus lambda completely overlaps the first block and partially overlaps the second block. So here is h of t minus lambda, and t plus 2 is between 4 and 6. So we have t plus 2 is between 4 and 6, or t is between 2 and 4. So y of t is equal to, it's the sum of two integrals, from 1 to 2, e to the negative t minus lambda plus 2, d lambda, plus the integral from 4 to t plus 2. And this one has an amplitude of 2, so this is 2 e to the negative t minus lambda plus 2 d lambda. Okay, we have one final region, and that region is where t plus 2 is greater than 6. So if I sketch h of t minus lambda, here's t plus 2. T plus 2 is greater than or equal to 6 means that t is greater than or equal to 4. And that region is also going to be the sum of integrals. It's going to be y of t is equal to the integral from 1 to 2, e to the negative t minus lambda plus 2 d lambda, plus we will also have the integral from 4 to 6 to e to the negative t minus lambda plus 2 d lambda. When you have these very complicated convolutions like this, it is sufficient to leave the integral in the final answer unless you're explicitly told to solve the integral. Okay, let's look at another example. Determine the output y of t of a system with input x of t equal u of t minus 2 u of t minus 1 plus u of t minus 2 and h of t equals sine of t u of t minus 2. As we've done on the prior examples, we are going to flip and slide h of t. So first let's sketch x of lambda. x of lambda is a step function that turns on time 0 at time 0 with an amplitude of 1. And then at time 1, you subtract off 2. So at time 1, it goes to negative 1. And then at time 2, you add a unit back. So it comes up and stops at the axis. H of t minus lambda is a sinusoid that turns on at time 2. So when you flip and slide it, it's a sinusoid at negative 2 that slides by t minus 2. And here's our crude sketch of a sinusoid. So now let's look at our various regions. The first region, as usual, is going to be when there is no overlap. So here's x of lambda, and here is h of t minus lambda. And this region, we have t minus 2 is less than 0. When t minus 2 is less than 0, that's the same as t is less than 2, and y of t equals 0. Our next region is going to be when t minus 2 is between 0 and 1. So here's our sketch. Here's x of lambda, 0, 1, and 2. And h of t minus lambda is between 0 and 1. Remember, this does not necessarily have to be to scale as long as you understand the overlap regions. So here we have an overlap here. So t minus 2 is between 0 and 1, or t is between 2 and 3, and y of t is equal to the integral from 0 to t minus 2 sine of t minus lambda d lambda. Our next region will be when t minus 2 is between 1 and 2. So first I sketch x of lambda. Then I sketch h of t minus lambda. And here is t minus 2 between 1 and 2. So when I have t minus 2 between 1 and 2, that's when t is between 3 and 4. And y of t is equal to the integral. It's going to be the sum again from 0 to 1, sine of t minus lambda d lambda, minus the integral from 1 to t minus 2, sine of t minus lambda d lambda. Okay, the final region is where h of t minus lambda completely overlaps x of lambda. So here is h of t minus lambda. And then remember, the leading edge is t minus 2. So here we have t minus 2 is greater than or equal to 2, or t is greater than or equal to 4. So it's the sum of two integrals again. Y of t is equal to the integral from 0 to 1, sine of t minus lambda d lambda, minus the integral from 1 to 2, sine of t minus lambda d lambda. Let's look at the final example for lecture 6-1 in class activity 4. Determine the output y of t of a system with h of t equal to t u of t plus 1 minus u of t minus 3 and x of t equal u of t minus 1 minus u of t minus 2 plus u of t minus 5 minus u of t minus 7. First, let's sketch x of lambda. X of lambda is 2 blocks, both of them with an amplitude of 1. One is on from 1 to 2, and the other one is on from 5 to 7. H of lambda is a ramp. So h of lambda is a ramp that turns on at time -1 and turns off at time 3. So since it's t, what you'll see here is that at -1 it turns on, and then it rises with a slope of 1, and it turns off at 3. So h of -1, you flip this first, means we now have a ramp that's decreasing, and it turns off at +1, and it turns on at -3. And finally, when you slide it, what you're going to have is this ramp where the leading edge is t+1 and the lagging edge is t-3, and this is h of t minus lambda, which equals t minus lambda. Okay, now we are ready to do the regions. Okay, let's sketch h of t minus lambda on our x of lambda regions. The first one is when there's no overlap. So here's my sketch of h of t minus lambda with my leading edge of t+1. Here we have t+1 is less than 1, or t is less than 0, and since there is no overlap, we know that for that region, y of t equals 0. Our next region is where t+1 is between 1 and 2. So here's t+1. t+1 is between 1 and 2, which means that t is between 0 and 1. So y of t is equal to the integral from 1 to t+1, t minus lambda d lambda. Our next region is where t+1 is between 2 and 5. When t+1 is between 2 and 5, that means that h of t minus lambda completely overlaps the first block of x of lambda because the trailing edge is at t minus 3. And since that's more than 4 wide, that means even when I'm at the 5, the trailing edge would still be at the 1. So this would be y of t equals the integral from 1 to 2, t minus lambda d lambda. Our next region is where t+1 is between 5 and 6. When t+1 is between 5 and 6, we still partially overlap the first block, and we're also partially overlapping the second block. So here's t+1 between 5 and 6, and here is the trailing edge, t minus 3. So y of t is equal to the sum of two integrals. The first integral is from t minus 3 to 2, t minus lambda d lambda, plus the second integral is from 5 to t+1, t minus lambda d lambda, and note that t is between 4 and 5 for this region. Our next region is where t+1 is between 6 and 7. When t+1 is between 6 and 7, I am completely off of the first block. So here's my trailing edge, t minus 3. Here's t+1. So y of t is equal to the integral from 5 to t+1, t minus lambda d lambda. And remember, this is the region where t+1 is between 6 and 7, or t is between 5 and 6. Our next region will be where t+1 is between 7 and 9, or t is between 6 and 8. So if we draw the graphic of what this looks like, here we have 7 and 9, and here, this is where h of t minus lambda completely overlaps the second block. So y of t will be equal to the integral from 5 to 7, t minus lambda d lambda. And then our next region is going to be where t plus 1 is between 9 and 11. And when it's between 9 and 11, what we have here is that the trailing edge of h of t minus lambda still overlaps that second block. So here's t minus 3, and here we have t plus 1. So this is where t is between 8 and 10. So y of t is equal to the integral from t minus 3 to 7, t minus lambda d lambda. And then I don't have a sketch for it, but our final region would be once h of t minus lambda completely moves over that second block. The final region will be where t plus 1 is greater than or equal to 11, or t is greater than or equal to 10, and y of t is equal to 0. And this concludes today's lecture on convolution examples.